Hey YouTube, today I will do topic modeling with the transformer based and as of now the most powerful tool called BERTopic. And I will apply BERTopic on a pretty famous dataset called arxiv abstracts to get the most important topics from that dataset. So first, a quick introduction on BERTopic. So BERTopic is a topic modeling technique that leverages transformers and class-based TF-IDF to create dense clusters, allowing for easily interpretable topics whilst keeping important words in the topic descriptions. And BERTopic supports guided, semi-supervised, and dynamic topic modeling. It even supports visualization similar to the very powerful package LDAVs. And BERTopic actually generates document embedding with pre-trained transformer-based language models, cluster these embeddings, and finally generates topic representation with the class-based TF-IDF procedures. And in this picture, what you see, they are the key algorithms that are used by BERTopic. So there are three main algorithms here, which is about first embedding the documents, then clustering topics, and then create topic representation from the clusters. So first about the embedding documents. Here, what BERTopic does is extract document embeddings with sentence transformers. Since the data we are working with are article titles or article abstracts, we will need to obtain sentence embeddings, which BERTopic lets us choose conveniently from among many sentence transformer models that are available. And then these cluster topics into semantically similar clusters. So here BERTopic create groups of similar documents with UMAP to reduce dimensionality of embeddings and HDB scan to identify and cluster semantically similar documents. And lastly, the last algorithm used by BERTopic is creating topic representation. So here it extracts and reduces topics with class-based TF-IDF. And TF-IDF, probably you already know that it allows for comparing the importance of words between documents by computing the frequency of a word in a given document and also the measure of how prevalent the word is in the entire corpus. And now if we instead treat all documents in a single cluster as a single document and then perform TF-IDF, the result would be important scores for words within a cluster. The more important words are within a cluster, the more representative they are of that topic. Therefore, we can obtain keyword-based descriptions for each topic. This is super powerful when it comes to inferring meaning from the groupings yielded by any unsupervised clustering technique. And here is the mathematical formula for class-based TF-IDF. So the frequency of each word T is extracted for each class I, that's why it is represented as Ti, and divided by the total number of words W, and also here Wi. So the average number of words per class represented by M here is divided by the total frequency of word T across all N classes, and that's why here we are summing over Tj from Tj to N. And that's your class-based TF-IDF formula. So basically all these are already included and very well optimized within the BERTopic package that we are going to use. And I have to say pretty much from 2022 onwards, when the BERTopic came into was first published and the code was available, it has become the single most important topic modeling technique across pretty much every domain. So if you are into topic modeling, you have to use this. Alright, so with that introduction, now let's get into the dataset that we are going to use for this topic modeling here. And the dataset is a huge collection of arxiv publications. And what they are saying is, for nearly 30 years, arxiv has served the public and research communities by providing open access to scholarly articles from the vast branches of physics to the many sub-disciplines of computer science to everything in between. Okay, let's actually look into the dataset. So remember, when you can download the dataset from here, and it is going to be a single file of a huge .json format. So these arxiv dataset and a metadata of 1.7 million plus scholarly papers across STEM discipline. This is the dataset about. So this is the .json file that I was talking about. It's 3.5 GB, and as you can see here, so this is a single entry in that .json file. So let's look at the first item here. So I have JSON format here. It's a dict format, and so each of these keys, so there are quite a few keys, and for example, I have ID, submitter, authors, title, comments, journal ref. For example, this key journal ref, that will contain the year of the publication, and that also is given with lot of extra string. So I need to take the last 4 digit to get the year of publication. And similarly, I have categories, that is a string, and it is given in a short form HEPPH, and we will see in a second that how we can get sense of these short form of categories, because if we go to arxiv's official side, they have given a detailed API where each of the short form of categories are expanded, and we can get the full form of these, and we actually need that to do this topic modeling. And here the important stuff, abstract. So this is the whole abstract of the first research publication. A fully differential calculation in perturbative quantum chromodynamics. Okay, I don't understand this text. This is abstract of the research paper for this very first item in the .json file. And obviously, I will put a link of the dataset in the notebook, which is available in the description of this video. That is in my GitHub repository. So first thing you have to install is BERTopic, and that's what I'm doing here. And then first thing I am going to do is to read the huge .json file with Dask, because Dask is relatively faster compared to pandas. And also remember these for this dataset, the great thing about using arxiv abstract is that the text is typically well structured and very nicely, concisely written. So for BERT-based embedding models, this kind of concise text allows the document representation to be a bit more accurate than what we would normally see. So that's a good thing about this dataset. And the first thing, I have already imported import docs.bag as db and also import JSON. And now let me read this .json file with Dask. So docs. Oh, have I think I need to just define this data file variable to be the source.json file, and that's my data file. Okay, and here. I just want to get the count of all the elements in the JSON file, and count.compute. So that's one of the method of Dask. It's an optimized. So what I have to give to compute is optimized graph, scheduler, optimization, but these are all optional. So just compute should be enough. So compute turns a lazy Dask collection into its in-memory equivalent. For example, a Dask array turns into a NumPy array, and a Dask data frame turns into a pandas data frame. The entire dataset must fit into memory before calling this operation. Okay, this is something to keep in mind. This is quite a large dataset, 3.5 GB almost. But anyway, Kaggle gives you 12 GB of RAM, so that should work. I have already run the cell. It's taking kind of almost a minute to run it. But in the meantime, let me define a few more things. So I am going to use Plotly. lot. Okay, it is still running. Alright, just finished running, and this has the file, our JSON file has 21,031,061 elements. That's a huge number of articles published in there. Okay, so now I am also going to check the top submitters in the publication. So for that, I'm going to use a lambda function. Submitter was the name of that key. So I am going to take from there the top 10 frequencies. True. This also going to take a little while, and frequencies, yeah, it should work. And these are the top submitters. We have the first one is just none, so that is a mixture of submitters. That is not important data point here. So the top submitters are EPTCAs, the CMS collaboration, Atlas publication, etc. Yeah, so that was just some basic information I fetched from the dataset. Now I am going to go to my VS Code to write some code. Okay, so this list, the one that you see currently, that's what I got from the arxiv official API documentation. The link is given here, right here. So there they have, just like I was saying, they have given the full name of these various terminologies for the category column in our dataset. So for example, astro-pH means astrophysics. So what was the thing that we were seeing in the very first one? So we had HEP-pH. Let's see. So that's for high energy physics phenomenology. So this category name is what I need to get. So now, right now, I'm going to write a little util function to pre-process and prepare the data. What was the name? Data. Wow. A line in F, yield. Note that the JSON file in the dataset are huge, and sadly Python has certain memory problem when loading huge JSON file, and that's the reason that I'm using yield here. And next I am going to do just print the very first data point from my data. So each of these element in the JSON file actually represent a published paper. So that's what I am looping over right now for paper in metadata. Loads. Items. Print F. And immediately after printing the very first one, just break from the loop. That should do. And when I ran this cell, this is the output. This just outputted the very first element from the data. So I have starting with ID and then journal ref, comments, abstract, category, etc. Okay, so now I am going to extract all abstracts published between 2000 and 2021, and also their titles and the years in which they were published, because my topic modeling will be based on these published paper between 2000 and 2021. So I'm first just I'm declaring some list variable which will hold these things: title, abstracts, years, categories. Okay, and now looping over for paper in metadata. Reference will be the year, public journal ref. I need to get the value, so year should be the as we saw in the original data, the last four element of journal reference, that's represent the year. So I need to get the last four characters. And now a little if condition, because the paper should be published between 2000 and 2021. Categories dot category map is this long variable, long dict. Paper dict. Split by a single space and take the 0th element. Sorry, I made a syntactical mistake here. Paper dig.get, and my list is ending here. Let's print the title. Abstract, and also the categories. And this is the output that I get for the length of title, abstracts, and categories, and they are all 1,049,158. So that many research papers published between 2000 and 2021. Alright, so with that, I'm ready to actually train my BERT model, because all the important parts that is required to feed the BERT model, that is all the abstracts of all the papers, are already in these abstracts variable, because this abstracts variable is actually a list, and that's what list of text, and that's what is needed to be supplied to BERTopic for training it. So let's start that. And also note that I'm going to make sure that the minimum topic size of our topics is 50, and I do this to limit the number of topics that could be generated. For example, if the minimum were to be 10, then much more topics could be generated that are most likely to be of little interest. Since we want large topics, I set it at 50. So let's actually from BERT top. Yeah. True. Embedding model. So for the embedding model, you can select from a whole list of sentence transformer model that has been very well explained in the BERT's official documentation. So there are almost like 20-30 sentence transformer model you can choose from. And for this one, I'm going to choose a pretty relatively large one called all MPNet base v2. And we can actually see the model card of this one in HuggingFace. But let me complete this sentence first. And min topic size, I'm going to keep it at 50. And this is the model card in HuggingFace for all MPNet base v2. So this is a sentence transformer model. It maps sentences and paragraphs to a 768-dimensional dense vector space and can be used for tasks like clustering or semantic search. Yeah, so that's and the model size, you can see the pytorch.model.b, it's 438 MB, so rather manageable. So with this line, I just defined the BERTopic class to be used here, an instance of the BERTopic class indeed. And next, I actually have to apply the fit transform on this model. So topics, and these are the output from the training. Topic model dot fit transform. That's the function that will train it. So this this will take a list of documents to fit the models on a collection of documents, generate topics, and return the docs with topics. Arguments, documents, a list of document to fit on, embeddings, pre-trained document embeddings. This can be used instead of the sentence transformer model. And Y is the target class. So in this case, the first one will be abstracts. That is the only argument that I'm going to provide. The rest it will select by default. And for the embedding, I have already defined it here. So when we run this cell, that's going to take almost like 25 minutes or so with a 16 GB GPU. So yeah, be patient here. And while it's training, let me carry on with the next set of codes, because after the training is over, I am going to get the actual result, that is actual topics from the training. So I have to see those topics, and for that you use get topic info method. So topic model get, and these are all coming from BERTopic. You can check their documentation. Also, I need to plot the topics. So my plotting will be visualize bar chart. To that you pass top and topics. Let's choose 9. All right, so after the training, this is the topics that were generated. And first, this -1 means that these are the outliers. So anything outliers are labeled as -1 in the topic column, and the rest are the actual generated topics. So for example, the 0 is collisions, AU, RIH, ion. Then topic 1 is dark universe, cosmological energy. Let's look at something Topic 5, lattice, quark, quenched, nuclear pairing, etc. Remember, these are research papers, so all this language may not make sense immediately to you, because here the original dataset was arxiv published papers. And the next line that we wrote here was to visualize a bar chart, and this is our bar chart, topic word score. So we can see here a very finely represented topics and the most important words under each topic. So for example, topic 0 has the most influential word under this topic 0 was collisions, AU, RIH, ion, heavy. Then topic 1, dark universe, cosmological energy, etc. And that kind of thing goes on. Topic 5, topic 4, topic 7, etc. So actually interpretation of these clusters is much easier if you are familiar with the content of the documents. For example, under topic 1, the most influential words for topic 1 are dark universe, cosmological energy, matter. So to me, it looks like some sort of theoretical astrophysics related research paper that the topic 1 is representing. So this brings to mind a general question that for each topic we have generated something like 10 words that best represent the topic, but can we determine how many words represents a topic? Like, is 10 words sufficient? Can we already have just one word to represent a topic? And to investigate this particular area, we have a tool in BERTopic. So to understand the amount of words needed to have a sufficient topic representation, we can show the decline of term score when adding new terms. So the idea here is that for each new term that is added has a lower term score than the previous one. Since the first term added has the best score for the topic, and the score goes on decreasing when I add more and more new terms under the same topic. Eventually, we reach the point of diminishing return, which is very similar to the elbow method used in K nearest neighbor. So right now I'm going to show these declining with a plot. And that code is, I need to use method from BERTopic, which is called the visualize term rank, and I have to apply that on topic model. So it's just a single line, visualize term rank. That is it. That is all. Everything is built in BERTopic. You just need to apply this method and you will see a beautiful plot. And if you look at the documentation of BERTopic, this is where I am, visualize term rank. So each topic is represented by a set of words. These words, however, do not all equally represent the topic. This visualization shows how many words are needed to represent a topic and at which point the beneficial effect of adding words starts declining. And that's the... Okay, let's go back to the official documentation once more. So it takes a log scale, whether to represent the ranking on a log scale. So by default, it's false. So I am going to see both without a log scale and with log scale. So this is a plot of these lines that visualize term rank, and here I'm looking at the actual scale. That is, I have not passed logarithmic scale as true. So we can see that here maybe keeping up to 7 is kind of okay, but after 3 it rapidly declines. That is, the first 3 words actually very much describes the topic. But now let's look at the logarithmic scale, because that will give a more realistic situation. And looking at this, looks like that it seems that the 3 words per topic are sufficient to represent the topic well. Any words that we add after that have seemingly little effect. And the next thing we are going to plot is this topic relationship. So intertopic distance map, and for that you just apply this topic model, visualize topic. So here, looking at this plot will tell you that which are the topics which are completely different, and some of the topics are actually kind of very overlapping, so they can actually be merged. For example, topic 20 and topic 6 here, they are almost similar, co-centric. So this plot actually maps our topics to a two-dimensional representation by reducing the topic vectors with UMap. and it's pretty important, pretty useful to decide which topics to reduce your dimension further, that is which topics you no more need in your modeling separately, or in your presentation, or in your ultimate decision making separately. Further few beautiful plots and useful plots you can build with BERTopic. For example, this one is visualize hierarchy, and it will show with these straight lines and also color coded the hierarchy between topics. And even more, let me see, what do I have? Okay, so I also have, you can also plot these heat map similarity matrix. So with visualize heat map, and you just pass the number of cluster and number of topics, and it will plot your similarity matrix between topics. And here in this heat map, some of the darker blocks actually represent the cluster of topics to be found that are somewhat or largely similar to each other. You can zoom in, and also if you hover your mouse over them, you can check their values. And for example, here in this block, the similarity score is pretty high, 0.87. And lastly, another very important plot you can do is plotting the topics over the time period, over the years. So although extracting the topics and their representation is interesting, we are missing some dimensional information, which is the time period. For example, some topics might not be relevant anymore, or some are gaining traction over the last years. And so that can be vital information when making your business decision. And for these plot creation, you only need 2 lines of code. That is all. So you already have our list of text, which is abstracts. We already have our topics, and you pass a time period here. So here I'm passing 10, which means it will create the topics over the past 10 years. And then you apply this method, visualize topics over time, to your topic model. Remember, again, this topic model is fully trained with the fit transform. So to this visualize topics over time, you pass these topics over time, these variable, and pass the top number of topics. I need 20. Width and height is just for plotting parameters, and this is a beautiful plot you get. And if you hover the mouse over these graphs, you will see the topic number. For example, the green ones was so important, so intense during the period of maybe 2005 to 2012. But eventually it declined drastically over 2012. So this is my topic 2. And similarly, more recently, this is topic 6, and this kind of was at the peak of its importance in 2020, and then also it declined quite rapidly. So yeah, these distribution over the time, over the past years is sometimes very, very important for your business decision. And the last class, or the last plot that I wanted to show here, is this one, topics per class. So I'm looking at the official documentation in BERTopic. So topic per class creates to create the topics per class, BERTopic needs to be already fitted one. That's obvious. From the fitted models, the C, TF-I, DF representations are calculated at each class C. Then the C, TF-I, DF representations at class C are averaged with the global C, TF-I, DF representations in order to fine-tune the local representation. This can be turned off if pure representation is needed. So basically what these topics per class is doing is that so when we do topic modeling, the number of topics are typically much larger, or relatively larger, than the number of categories that was already there in the dataset. And these topics per class helps us to find and understand certain subcategories that might exist in the data, and also specifically plot that how many topics were found out by these BERTopic modeling for each original categories that was there in the original data. And to get that, you just need 2 lines of code. So topic model dot topics per class, you apply this topic per class here, and to it you pass the abstracts. That's what the documentation needed. The first argument is a docs, which is a list of string, the documents you used when calling either fit or fit transform. Yeah. So that's what we are passing, and classes are the original categories in our document, in our original data set. Remember, the original arxiv had a category key, and that will show you the category. That is whether it's astrophysics or whether it's hardware architecture, things like this. That is these things I'm talking about. These are the original categories defined in the original data set. And then the next line of code, just this one. Topic model that visualize topic per class. To that you pass these topic per class variable. I need top number of topics 10, width 900, and that's a beautiful plot you get. So you can see that under the astrophysics, number of topics is 0 word. So these are the topics under these astrophysics category. Similarly, under these mathematical physics, these are the topics. And as the official documentation says that these topic per class returns a data frame that contains a topic, words, and frequency of topics for each class. And that's what is plotted here. And you can also see the frequencies in the horizontal axis. So we can see the maximum number goes beyond 800 for these, I think that's plasma physics or information theory, maybe. Probably it is information theory. That's where the frequencies are highest. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So see you in the next one. Thank you very much for watching.